Today we'll be working on the following problem. Can we partition the R plus, the set of all positive real numbers, into two disjoint sets, E1 and E2, each of which is closed under addition, which means for all x and y in E sub 1, then the sum is also in E sub 1. That's what we mean by closed under addition. So pause the video if you want to work on this problem by yourself. Okay, this is a very interesting one. Basically we're going to prove the answer is yes. Yes, by assuming axiom of choice, or equivalently Zorn's lemma. Okay, so first, let's see if we have this partition. So clearly 1 should be in one of it. Let's see if 1 is in E1. Then we claim for any P over Q, the rational numbers, positive rational numbers. The rational numbers is also in E1. Why? So we want to show P over Q is also in E1. Otherwise, if P over Q is in E2, because E2 is closed under addition, so we can have P over Q plus P over Q times. It should be in E2 too, right? This means P is in E2. But since 1 is in E1, so if you add P times, you also have P is in E1, right? That's impossible. So what we have shown is Q plus the positive real number has to be in E1, right? And then you can have so if we have such partition, then we can write is all the rationals union sum of irrationals, and then this will be your E1, and then union the rest of irrationals, right? That will be your E2. So you can from this you can add some irrational into the positive rationals Q plus and make it bigger and bigger, but then always E2. Clearly E2 cannot be the set of irrationals, right? So if E2 is the irrationals, E2 is not closed under addition. For example, pi in E2, you can have a 4 minus pi is also in E2, but there's some. It means 4 is in E2, which impossible, right? So E2 has to be. E2 cannot be the entire set of irrationals. Okay, now how do we find this E2? So basically we are building this E2 by using the Zorn's lemma. So in order to apply the Zorn's lemma, we first define the partial order set to be the set of F is a subset of irrationals. F is closed under addition. And then the partial order, because F is a set of a collection of sets, right? So the partial order is the set inclusion. Okay, so one set is a subset of another set, the inclusion, right? So now, in order to apply Zorn first, P is not empty, right? Why? Because, for example, the multiples of pi is in P, right? Because they're all irrationals, and then it clearly is closed under addition because they're all multiple of pi. Pi is irrational number. So and now the second, let this T be a chain in P, right? Meaning like T is totally ordered, and then the order is the inclusion, be a chain in P. And now how do we find the upper bound of T? So if we let F is the set of the union, all the set in T. Remember, T is a collection of sets. This T, right? So F is a upper bound because you basically union everything in T is upper bound is upper bound is the upper bound of T, right? So any T in T, the bigger T, of course, T is a subset of F. So F is the upper bound, but we need to make sure like F is a closed under addition, which is obvious, right? So because if any xy in F, so there exists like G and H, for example, G and H is in this T. Now you have X in G and Y in H. But since T is a totally ordered, so we have either G and H are comparable. So based on the set inclusion, so either G is a subset of H or H is a subset of G. So let's assume like G is a subset of H. Then we have both X and Y in H. But from the construction, right? H is a H in P and H is a closed under addition. So this implies X, the sum is also in H. So F is indeed an upper bound. Now apply the Zorn lemma. We can have apply Zorn's lemma. There exists a maximum element in P. So we can find there exists, let's call this F, a maximum of P, right? So it means any subset, it's any member of P, it's a if this member and F are comparable, then it has to be a subset of F. Now we claim this F is actually being part of the partition. We claim equals to the rational numbers. I mean okay, we say the minus F, this set union F. this is our E1, this is our E2. Basically, this is the partition. And the F is clearly closed-ended addition, right? Because that's a member of P. So all we need to show is E1, this E, or we can say this is E union F. Let's put it this way. So we want to prove, we claim this is a partition, is the partition. So all we have to show, we need to show E is closed under addition. Right? So let's see, let's pick X in E and Y in E. We want to show X plus Y. X plus Y is also in E, right? Then we're done. So let's see, we're breaking into several cases. If X is rational number, Y is also a rational number, then this is a simple case, right? X plus Y is a rational number, which is in E, right? So second case could be, let's see, X is rational numbers, but Y is not in, and Y is in E, but Y is in E, and Y is irrational, right? So now we want to prove X plus Y is also in E. So suppose not. Suppose X plus Y is some F, which is in F. Remember, F is the maximum member of P, right? So suppose this. Then let's if this, suppose then we have, if we then consider this set. Let's see, F prime. We want to F and the union the multiple of Y. All the multiples of Y. And now we also union all this F plus NY, the set of all this number in this format, where F is in F and N is a natural number, right? So all the multiples. And now you can verify, clearly F is bigger than F prime is bigger than F, and it's not equal to F because Y is in E, not in F. So it's not, so it's a bigger one. But then also it is close under the addition, right? All the multiple together, and then this, it's F prime is close under addition. But we have to be careful because this could be, but F prime also from this, we also want to make sure it is a close-ended addition, but a subset of irrational numbers. So the only thing we need to verify is this has to be irrational. So F plus NY for any F and N has to be irrational. Is irrational. Why? Because if this is rational, so we have F plus N, because Y is let's use this. Okay, just the number. We use f prime. Okay, x plus y is f prime. So we have f prime minus x, right? And this is f plus n f prime minus nx, right? So because f and f prime are in bigger f, so this is irrationals, and then x is rational, nyx. So this is irrational, because you have irrational minus irrational is irrational, right? So now what is why we have a contradiction, right? So f prime is contradicts to the maximality of f, because we find a bigger one, right? So the third case is both of x, y, x in E, y in E, and x, both x, y are irrationals. Now we also want to show like x plus y is in E, right? So in this case, let's also assume like if x plus y is some f in this f. So now again, like in the case 2, we want to construct a bigger set to reach the contradiction, right? So in this case, like let's say if this in f, so we want to consider all the numbers here. So let's see, f prime plus nx. F prime is in f, n is all the natural numbers. We consider these two sets. Also, like we use another like g prime plus m of y. G prime is in f, also natural numbers, right? Well, we consider this if this is a subset, if this set is a subset of irrationals, if this is a subset of irrational, no, then we define f is the same as before, right? As in the case 2, the previous case, we define this nx, n is in n, and union all this f prime plus union these two sets. Then again, f prime is bigger than f. We reach a contradiction, right? So, or if any of this is irrational, we do the similar thing. So, and then we have a bigger f prime. So now, if not, if there exists f prime and n such that f prime plus nx is a rational number, and then again the same g prime m such that g prime plus m of y is also in q plus rational numbers, right? So if this case, then we can pick n to be the minimal. pick n to be the, because you have this, you can have n is a natural number, so you can always pick the smallest n, such that there are some f prime plus n x is in rational, and then pick m to be minimum. The same, right? So now if n equals to m, what do we have? Then we have f prime plus nx plus g prime plus my is in rationals, right? Because both of them are rational numbers, so the sum is rational number. But then if n equals to m, so the left hand side, this one, it becomes f prime plus g prime plus n times x plus y. And this is f prime plus g prime plus n times, because we assume x plus y is f, and which is also in f. So this number is actually in f, contradiction. So it cannot be in f and q plus a disjoint, right? So this is a contradiction. So now if so then n and m, if n greater than, so one of them is bigger, right? So without the loss of generality, we assume n is bigger than m. But now in this case, we can write nx to be in this format. So f prime plus mx plus n minus mx, right? So now if you add a g prime plus my, adding this to this set, so adding on both sets, you have and then we assume this one is a rational number, and this is also a rational number, right? So if you add them together, what do you get? You get f prime plus g prime plus m and x plus y plus n minus mx is also irrationals, right? Okay, this is what. So x plus y is small f, and then this part is in f, right? So there's a bigger f, but n minus m is strictly less than n. So this contradiction contradiction to the n we picked, because we pick n to be the minimum. So we have we arrive a contradiction, right? So this 3 case covers all the different cases of x plus y. So which therefore for all x in E, y is in E, x plus y is also in E, right? So from here, so I have all of this. So actually now we have this partition. So E union F is partition, is the partition, right?